A very good evening, good afternoon, and good morning to all. I, Dr. Pallavi Saxena, SSC member of iLEAPS, and Dr. Samina, iLEAPS IPO, welcomes you all in our 10th talk of iLEAPS Global Colloquium Series, episode 4. So, with a very good response received from the speakers, the previous speakers, and the attendees, we have decided to continue this iLEAPS Global Colloquium series in 2025 also. We have started this series in 2022. So before I go further, let's have a brief look about iLEAPS, what iLEAPS is. So iLEAPS is Integrated Land Ecosystem Atmosphere Processes System, and it is a global research project of Future Earth. iLEAPS provides understanding of how interacting physical, chemical, and biological processes transport and transform energy and matter through the land-atmosphere interface. The prime purpose of this colloquium is to introduce the scientific society, people with the distinguished and significant work of eminent scientists from different parts of the world. It is a very bright opportunity for the ECRs to interact with the distinguished speakers and establish the bridge between the ideas and the knowledge through this platform. So our today's speaker is Professor Lisa Emberson, who is a professor of environmental science in the Environment and Geography Department at the University of York in UK. She has over 20 years experience in the field of modeling soil plant atmosphere systems for assessment of the risk of impacts of air pollution and climate change. She has developed research activities in Europe, Africa, Asia, and Latin America, investigating the effects of the range of air pollutants and climate change on both agro and forest ecosystems, with a view to investigating the subsequent impacts on yields and productivity, and consequently social and economic systems. She continues to have an active research role in Europe, developing deposition methodologies for use within the UNECE Long-Range Transboundary Air Pollution Convention, and also sits on the Scientific Advisory Panel of the Climate and Clean Air Coalition, providing advice on the benefit of action on short-lived climate pollutants in relation to agricultural productivity and ecosystems. So today she will talk about developing modeling methodologies to estimate ozone impacts on crops and forests, what is its current status and future needs. And this talk will describe about the combination with the risk assessment methods for crops, forest, and identify the challenges related to them. So I again warmly invite Professor Lisa to put more light on this topic. Now, Professor Lisa, the floor is all yours.
Okay, thank you ever so much. I'm hoping that you'll be able to see my screen and my slides. There we go. Is that working?
Yes.
Excellent. Right. Okay. So thank you ever so much for inviting me to come. It's a really good opportunity to for me to sort of run through some of the different methodologies that myself and others have been developing over the past decade or so. And also, I think, to raise some questions that I have over some of these methodologies, and perhaps get some ideas from other people who are here in terms of the future directions that we need to take for this work. So, if I can move forward, that would be good. Oh, there we go. So I guess it would be, first of all, interesting just to sort of lay out the ground in terms of how big a problem ozone is for vegetation. And I thought I'd just show these two little diagrams. This is obviously the chemical notation of ozone, which you're probably all quite familiar with. I just wanted to introduce this other little character here. I don't know whether people will have come across this, but Pallavi, in the introduction, you mentioned the work that I do within CCAC, the Climate and Clean Air Coalition. They have developed this tropospheric ozone character in the hope to raise awareness of superpollutants, of which tropospheric ozone is one, in the hope that this can raise awareness at the sort of policy level in terms of identifying some of the multiple benefits that we would see if we were to reduce ozone concentrations, both in terms of greenhouse gas emissions and the effect on climate, but also ozone as a pollutant impacting human health and impacting vegetation. And I think one of the things that's going to be quite interesting for our community going forwards is to get a much better estimate of exactly what impact ozone is having on vegetation so that we can support the policy process. So whether or not you like the term pollutants, I think it's sort of here. And I think policymakers are starting to be more aware of ozone as a problem and wanting guidance on what we can do about it and what kind of benefits we might see if we do. Come back to this towards the end. In terms of the evidence that we have, which gives us an idea of the size of the ozone problem and its effects on vegetation, we have to start off with experimental evidence. The map here gives you an indication of really just the ozone monitoring that goes on, and you can see that there's quite a difference in the density of those ozone monitoring sites across the world. Lots of areas where we really don't know too much, even just about the ozone concentrations. That gets even worse when we're starting to think about the experimental evidence that we have to give us knowledge of how ozone is impacting vegetation. There tend to be two main types of study that are used: open-top chambers, which are shown here, where you can fumigate a crop or a small tree over the course of its growing season and look to see what the response is to that fumigation. Or you can also use free air concentration enrichment trials, where you can again fumigate sort of more naturally occurring commercial field with elevated ozone concentrations as well. Those types of experiment have sort of followed the elevated ozone concentrations around the world in time. So we had studies going back into the 1980s across North America. 1990s, we had quite a lot of studies in Europe. And then now more recently, from the 2000s and onwards, we've got a lot of studies coming out of Asia. I've kind of highlighted East Asia here, but we also have a lot of studies and work in South Asia as well. And the kind of big issues that we have here is that there are very large regions around the world where we really don't have any experimental evidence. So we have to assume that the data that we do have is transferable to those other regions, those data poor regions. And we do have some FACE experiments. I've sort of tried to give an indication of those that I know have existed. A lot of these are no longer running, but they're obviously much more expensive, so they tend to be more difficult to bring in across the world. But probably the main difference between open-top chamber experiments and FACE experiments is that with an open-top chamber, you can actually get back to zero levels of ozone, so you can really look at clean air. With FACE experiments, it's sort of more considered to be closer to sort of commercial field conditions, but you can only ever increase ozone concentrations above the ambient concentrations that you have. So it's a slightly more limited experimental method that you can use. Anyway, that experimental data, quickly whiz through this, has given us an indication of the types of effects that we see in terms of ozone on crops. I've highlighted crop yields here because that tends to be the one that we focus on and we talk most about. But this list is really just to show that there are a whole load of other effects that ozone has on arable crops. And all of the experimental evidence that's been collected over the past sort of 30 or so years, there have been a number of really good meta-analyses that have been developed over the past 10 years, trying to pull all of that information together. Just to give an example of one of these, so this is Feng and Kobayashi back in 2009. quite a nice study because they looked at a number of different crop species and they related changes in yield metrics from a baseline of around about 26 ppb ozone concentration to an increase of around about 30 to 50 ppb, which is sort of common across parts of the world where ozone is elevated. And you can see the size of the effect. We're seeing effects in some of these yield parameters that are anywhere between sort of 5 and 15 to 20% change in relation to that elevated ozone. And we see things like bean come out as being particularly sensitive species. And we can also get estimates of the ozone effect on yield losses for those different crop species. Same sort of thing for forests. This is just taking data from Aspen Face, which is a study that ran from 1997 to 2004. The nice thing about this study was that it didn't only just look at ozone, but it also looked at elevated CO2 and then the combination of ozone and CO2. But again, we could see very obviously impacts of ozone on growth and biomass, but also impacts on a whole host of other effects. So I think it's just worth bearing in mind the fact that there is a lot of experimental evidence to show that it's not only crop yield and it's not only forestry biomass that is being affected by ozone. So this gives us information at the site-specific level, and really what we need to do is try and scale up that information to make an estimate of the regional or global impacts that we're seeing from ozone. And the most traditional and best used method, if you like, for doing that is to use this kind of dose-response relationship. So here these points give us an indication of all of those experimental studies where we're pooling the results from those experimental studies onto this dose-response relationship. We can put a regression through those points so that we can produce a dose-response relationship that can be used with other data describing a kind of field of ozone concentrations over a region or over a globe, so that we can get an estimate, broader scale estimate of the response of the different receptors, crops and forests that we might see. We can also use this kind of dose-response relationship to identify a critical level, and then we can apply that critical level to also give us an idea of the regions, the global areas where we're seeing exceedance of a critical level or some quality guideline. And the big question here is, which ozone metric should we use? And this is almost a question out to people. There are a whole load of different ozone metrics that are in use and have been in use over the past 10, 20 years, but there hasn't really been any consensus on which of these metrics is best to use for a variety of different questions that we might answer. Just to run through what those metrics are, so this is just an illustrative profile of a hourly ozone concentration over the course of a year, and we can describe this as an annual mean or an annual daylight mean if we're interested in plants, or we can describe it in the way that the metrics that are currently used do at the moment. So here we've got identifying a growing season daylight mean. So this is the M7 and the M12 metric. So we emphasize the growing season because that's when the plant is physiologically active, as well as the daylight period. M7 just means that you're looking at 7 hours over the daylight period, and M12 means you're looking at 12 hours over that daylight period. And then similar to this growing season metric, we also have W126, which just adds weight to the higher concentrations over that period. And then we have two accumulating indices. So AOT40, that will accumulate any of the ozone concentrations over 40 ppb over that growing season. And then the one that I've sort of been most involved in developing has been this POD-Y metric, phytotoxic ozone dose over a threshold. And the difference here is that now we're starting to define a metric that actually estimates the ozone that is taken up by the stomates on the leaves of the plants, and that's the ozone which is actually causing damage. So we can avoid disconnects between ozone concentration and exposure and concentrations that don't actually get taken up by the plant and cause damage. So if you look at these metrics and you develop dose-response relationships from them, then interestingly you find that those dose-response relationships are fairly similar in terms of their statistical robustness. So most of the R-squared values associated with those relationships are very similar. But if we apply these metrics, we actually get quite different results in terms of some of our responses, such as relative yield. So this is a study by Amos Tai. This is for wheat, and he used the same ozone concentrations produced globally from a global atmospheric chemistry transport model, but then produced the metric from those ozone concentrations and then applied the metrics dose-response relationship to produce an estimate of relative yield. And you can see here that AOT40 is giving you really quite high estimates of yield losses. W126, not quite as high, but still high in some regions. POD3, a sort of intermediate estimate of yield loss. And then M7 is not showing very much yield loss at all. So everything else is the same. That difference is just due to the metrics that are being used. And they didn't just look at wheat. So this is, again, from their paper. This is a summary of that wheat data by different regions. So this is East Asia, Europe, South Asia, and the US. And then this is showing how for wheat, that AOT40 metric is giving you really high yield losses. If you look at the same situation for soybean, now you see that M7 is giving you really high yield losses compared to the other metrics. And then if you look at maize and rice, then you see that the metrics are actually giving you fairly similar estimates of yield losses across those regions. So it sort of begs the question of why are we seeing such differences when the dose-response relationship itself is actually giving us quite similar statistical robustness in terms of the response that we might see under experimental conditions, but when we apply it globally, we see those big differences. And this might be one reason why we're seeing this. I'll try and explain what you're seeing here. So we've got two different sites. We've got one site in the UK and one site in Hong Kong, China. And you're looking at data which is the difference from the start of a period to the end of a period. So 1989 to 2013 for the UK, 1995 to 2015 for China. And if we look over here, then you can see how the ozone concentrations fitting into different bins have changed in the UK over that time period. So what we've seen is an increase in the more chronic ozone concentrations and a decrease in the peak ozone levels over that time period. And for China, we've seen just an increase in all of those bins of ozone concentration. And we can relate that to metrics. I've picked out the vegetation metrics here. And again, you can see that for the UK, all of those metrics have decreased over that time period, aside from the M12 metrics, which have actually increased. And that's because we've got this increase in more chronic ozone concentrations. By contrast, in China, all of those metrics have seen an increase. So I think the take-home message here is that we really need to understand the ozone concentration profile to understand what kind of estimate of damage our metrics are going to pick up, and also to think about which metric we do actually need to be using for which specific question we might be trying to ask. So in terms of that ozone concentration profile, we need to consider whether our ozone climate in the region of interest is more likely to have peaks or chronic ozone concentrations, and also think about how our mean ozone concentration might relate to any threshold that exists in the metric. So for example, that 40 ppb in the AOT40 metric. And then also in terms of thinking about the question that the metrics should be answering, for example, what's the effectiveness of an emission reduction strategy? We might want to consider, are we looking at local NOx and VOC emissions that might reduce peaks, or are we thinking about global methane emissions that might reduce more chronic ozone concentrations? And one of the other things that I'm sort of quite intrigued by is how trends in ozone concentration and the ozone concentration profile that we might see might be related to changes in our the sort of dynamic ozone climate that we have, and whether it's VOC or NOx or aerosol limited. That could be an interesting question to look to in the future. We can also ask, is there any evidence to suggest which of these metrics performs better? I think there are only 2 studies that have really looked at this. This is one from Gina Mills back in 2011. They compared AOT40 with POD3, and they actually tried to give an indication of whether the areas that the metric would suggest would be those areas that you see damage were actually areas where damage was seen using a biomonitoring experiment. This is across Europe, obviously, as you can see. So for AOT40, each of these little black dots gives an indication of where damage was seen in this biomonitoring experiment. But for AOT40, the areas in green, that metric would suggest you shouldn't have seen damage there, but the data suggests or shows that we did see damage. By contrast with POD3, again, it's the areas in green where you would not be expected to see damage. And in this instance, then the POD3 is actually giving you what would seem like a better estimation of the spatial distribution of the actual damage that is seen. So that might suggest that POD3 is a better metric than AOT40. But then we can also think, well, does this kind of flux-based metric actually give us all the information that we might need from a metric to really understand the impact of ozone on vegetation? So the flux-based metric does give us some additional information. It helps us to understand how the impact of certain factors which we know determine the sensitivity of different species to ozone will be taken into account in terms of estimating ozone uptake. So we've got things like species physiology, phenology, and meteorology. So we can start to open that black box to understand how interacting factors are affecting ozone sensitivity. But there are a lot of interacting factors that we know will affect sensitivity, and flux metrics can't take all of these into account. Just to run through some of these, so this diagram is showing you where we're seeing ozone damage. So we have ozone uptake that affects photosynthesis, that can affect also early senescence in terms of your crop, so you get reductions in crop biomass and yield. It can also affect the length of the growing season, which will determine the kind of impacts that you see. But the mechanisms by which ozone is causing that damage are also affected by other factors. So we have things like CO2 concentration in the atmosphere will affect gas exchange, and that if it's elevated, might limit the amount of ozone being taken up. That gas exchange will also affect the amount of transpiration that we have coming from the system, which, along with precipitation, can affect the soil moisture that you have in the system, which can again affect gas exchange. And then also we have other pollutants normally in a situation where you might have elevated ozone, you might also have elevated aerosol. And this will have effects on the amount of radiation coming into the system, and again, will change, therefore, the stomatal conductance. So it's a complex pattern. There's a lot of different factors going on here, which will be determining ozone sensitivity of different crops and tree species. So do we need a different approach to ozone risk assessment? And one of the things that I've been working with a group of people called AgMIP, which is basically a group of crop modelers that are comparing and contrasting their different crop models using crop model ensembles to try and answer questions about, for example, how climate change is going to be affecting food supply into the future. We've been working with them on what we call an AgMIP ozone activity. So essentially what this will do is take these open top chamber experimental data, and rather than using this dose response function to give us an estimate of potential yield loss, but just accounting for ozone concentrations, we can now rather use a crop model so that we get an estimate of the ozone impact, but we can also estimate the effect of other abiotic climate stresses on crop growth. So we're getting to the point where we will hopefully soon be submitting this AgMIP ozone paper. What we've done in the paper is we've used around about 12 different crop models, which are listed here. Different types of crop models, some are photosynthesis and some are radiation use efficiency models. They have different time steps, and perhaps the interesting thing to notice about these crop models is that they also use different ozone metrics. So most of them will use stomatal flux, but there are still some that are using concentration-based metrics, which brings another sort of dilemma into some of the circularities, I think, in terms of which metric should we really be using for this kind of assessment. So we've developed the data sets. We've sort of gap-filled open-top chamber data sets from 4 different countries. We have a number of different years in these data sets, a number of different cultivars, a range of different treatments, and we're seeing yield losses in the data sets, which are quite substantial, so we can calibrate the models to really be sensitive to ozone treatments and ozone conditions. And the protocol that we have, we're using a calibration protocol, so we calibrate the crop models for ambient ozone and then stress, so additional ozone concentration conditions. And then we evaluate those crop models to see whether the models can work across different years and therefore across different meteorologies and different ozone concentration profiles, but also across different cultivars as well. Some initial results. So this is data from Bangor for wheat showing leaf area index. So these are the observed data are these circles, and then you can see how the models are performing at simulating the leaf area index for that experimental condition. So some of them are really not doing all that well. But if we were to take the crop ensemble result, then we would probably be getting pretty close to the leaf area index that was observed. And then if we look also at how the models are estimating yield differences, again, we can see that some of the models are doing quite well, but we have some models underestimating and some models overestimating those differences. So we're kind of at the stage where we're trying to understand both the experimental data sets, but also the models themselves to understand where some of those models are struggling, and then also whether if we use an ensemble of these crop models, are we getting a good enough result so that we can say with some confidence that the models are able to simulate the effects of ozone and other abiotic stresses on yield. The idea is that we would get to that point, and then there would be an AgMIP ozone phase 2. So this would then be taking those calibrated and evaluated crop models and applying them across the globe. So the idea here would be to then evaluate the climate change and ozone impacts on current and future global agricultural production. So not only looking at wheat, but also looking at some other crops. The goal being that we could then provide support to understand how we might mitigate ozone problems for future global food production, but then also to raise awareness of global ozone impacts in the agricultural community and hopefully continue the development of these crop models. So this study would simulate both historical and future sort of runs. So we'd go from 1985 out to 2100 using different climate scenarios, and the outputs would be phenology, above ground biomass and yield. And there's a full protocol that exists already. Jose Guarin of NASA is the person leading this study. And if you wanted to get any more information about that, you can have a look at this protocol and get in touch with either myself or Jose if you'd like to be involved. Just to run through some of the different models and show some of the capabilities of these models. So this is the DSAT N-wheat crop model. This is a radiation use efficiency type crop model. Essentially, it uses radiation and it uses two factors of photosynthesis and early senescence to simulate the ozone damage effect. And interestingly, this crop model is now using the M7 metric. So basically, once you get past a certain level of M7 over the course of the growing season, you start to see a reduction in photosynthesis or an increased early senescence. And the model has been calibrated so that we have a sensitive variety and a tolerant or intermediate variety. And the results so this is Jose's model, the results that Jose found with this give some sort of credibility that the model is able to sort of provide a good simulation of relative yield losses due to this M7 ozone metric. So here we've got 4 different crops again. The black dotted line gives you an indication of the standard viable relationship that is used in those with that M7 metric to make those estimates of relative yield that I showed right at the beginning. But with Jose's classification of different cultivar sensitivity and application of his DSAP-N wheat model, you can see that these sort of more wiggly lines are actually his estimates of how those different cultivars with different sensitivities would respond to that amount of ozone concentration characterized as M7. And he's getting a pretty reasonable estimate from the model, which is similar to the observed data that you see. So starting to be able to identify different sensitivities of different cultivars and be able to model those in terms of their response to ozone. So that's a radiation use efficiency model. We also have other models which tend to be termed as photosynthetic-based crop models. So these look at biochemistry or model the biochemistry of photosynthesis in the leaf and then scale that up. One of the models is the one that we've been developing here. It's called dose crop. It's actually based on well, the dose model that we have, but then also it uses the sort of canopy carbon allocation algorithms from the Joules model. And essentially what it does is it takes met data, ozone data, brings it down to the canopy, and within the canopy uses an estimate of photosynthesis and stomatal conductance to give us our stomatal ozone flux and therefore our damage on photosynthesis at different canopy layers, which are then accumulated across the canopy, which then feed into a net primary productivity estimate, which is split out to different canopy components, so root, harvest organs, stem, and so on. And then that gives us an estimate of yield modified by these ozone effects, but can also give us sort of real-time estimates of leaf area index and crop height. So it's quite a complex model. And it's quite interesting to sort of look and see how these different models compare to each other. So this is a study published a couple of years ago, looking at 3 different models. WAFOST, which is the sort of European JRC model that is applied for crop seasonal forecasting across Europe. Bental C2 is another photosynthetic-based model, and then we've also got our dose crop model. And we applied this model with some data from Spain, which looked at both an ozone treatment, so a clean air, and an ozone increased air, and then also a drought treatment. So we had well-watered and droughted conditions. This just gives an indication of those 3 different models. So this is the green, the blue, and the yellow line, and their ability to simulate leaf area index, both the kind of total leaf area index and then also the green leaf area index, so allowing for senescence. So the models are performing reasonably well in terms of being able to do that. But obviously we're interested in really understanding how those crop models are able to simulate yield under those different conditions. So here we've got our sort of control condition. So this is our charcoal filtered and well-watered treatment, and these are the yields that we would be seeing. And then we ran the models to see if they could cope with the effect of ozone, the effect of drought, and then the combined effect of drought and ozone. And I think what's nice is that it does look like those models are really quite good at estimating those effects of those different stresses. And interestingly, they're able to estimate the combined effect of drought and ozone, which is less than additive of those 2 other effects quite well. So just in the last sort of couple of minutes, I thought it would be interesting just to think about whether there are other types of ozone damage that we should perhaps be concerned with. So we have had a tendency to focus on crops and on crop yields. We've looked a little bit at forest biomass as well, but I want to sort of think a little bit about whether, rather than just looking at the quantity of the crop yield that might be damaged, should we also be concerned about crop nutrition? And then also think about forest biomass, but in relation to carbon sequestration. So in terms of crop nutrition, again, within this dose crop model, we've developed a nitrogen module. So what that does is try to work out what the effect of ozone is on nitrogen partitioning over the course of a wheat growing season. This shows you what that partitioning generally looks like. So we've got nitrogen, the nitrogen fraction held in the leaf, the stem, and the grain as it progresses over the course of the growing season. So we start off with very little in the grain, and then over time, nitrogen moves from the leaf and the stem into the grain. And what we know is that ozone is affecting this remobilization or movement of nitrogen into the grain. And it does that in 3 different ways. So we know that ozone is changing the onset and the rate of leaf senescence. So it's changing the time period over which you can start to have that nitrogen mobilizing itself into the grain. It's also affecting leaf senescence. So it will bring that leaf senescence earlier. And overall, that affects the amount of nitrogen that is remobilized into the grain. And that's important because you need that nitrogen in the grain to give you a nice, nutritious grain in your wheat crop. So this was work done by Jo Cook. She developed this nitrogen module. We used data from CH Bangor solar domes for wheat, 2 years, 1 cultivar, which had an ozone fumigation from the stem elongation to harvest. And you can see here the effect. So these are the 2 different years. But essentially, this is the effect on the grain nitrogen content under low ozone and high ozone. So as you have higher ozone, you're reducing the amount of nitrogen in the grain fairly substantially. And then what Jo did, which I think was also quite interesting, was take this dose crop N module simulation of changes in grain nitrogen, convert that into a change in amino acids. And here she was looking at the indispensable amino acids, and in particular lysine and methionine, which are known to be impacted by ozone. And then she also changed that sort of concentration of amino acids into an FAO score of recommended protein quality in a foodstuff. So it kind of gave quite a nice framework to be able to go from a change in nitrogen content in the grain to an actual change in dietary protein quality in a particular foodstuff. This was quite pioneering work, and I think one of the real things to say is that we really didn't have very much data to parameterize the model. So although the model framework is set up and it seems to work, we need more data to make sure it's giving us sensible results. And one way of doing that would be any future experiments that are conducted. If they can measure nitrogen and protein concentrations in leaves and stems, then that in itself would give us some really useful information to further develop this model. And then the final thing just to talk about is thinking a bit about forest biomass and carbon sequestration. So there was a paper by Sitch a number of years ago that showed that ozone impacts on gross primary productivity had been quite substantial over the period in which ozone concentrations have been increasing around the world, and that had reduced the amount of carbon held in the land system, and that the effect of that in terms of then increasing the amount of CO2 concentration held in the atmosphere actually meant that the indirect effect of ozone was greater than the radiative forcing that would have been caused by ozone itself. Given the fact that ozone is the 3rd most important greenhouse gas, that's quite an important finding. So to be able to do that kind of work, you needed to have land surface exchange ecosystem models such as Joules, which limited the opportunities to be able to use things like dose response relationships to get an indication of how carbon sequestration might be changing year on year. So the work that we did basically reanalyzed the dose response relationships. These are flux-based dose response relationships. Normally for forest trees, we get an estimate of the whole tree biomass, which is problematic because we can't use that to say how the effect of ozone on year-to-year changes in biomass of forest trees. So we reanalyzed the data so that we we're able to get an estimate of the ozone effect on gross annual increments, so how much wood is laid down each year in the forest tree. We did that by using a kind of standard Richards equation to describe how biomass is accumulating over some time, 0 to 100 years here, in different tree species. We're just interested in this area because most of these ozone fumigations are performed on very young trees. So with this reanalysis, we're able to look at the difference from the start to the end of the ozone fumigation period in terms of biomass held within the tree. And then using this equation, we can work out what the ozone effect is on year annual growth rate. We can pool all of that information into dose-response relationships so that we can then produce an estimate of the relative gross annual increment rather than the relative whole tree biomass effect of ozone. And we can apply this using kind of standard methods where we have ozone concentration data, meteorological data. We can run the dose model to estimate our stomatal ozone fluxes, which give us our pod values, and then we can use that pod value to modify the gross annual stem volume increment. We can allow for natural and total fellings so that eventually we can run through this and get an estimate of the ozone impact on the annual net change in forest standing stocks, and then do some mathematics to work out what the actual carbon stock changes would be. So we applied this across Europe. So we've got a situation where we can estimate the ozone effect on this gross annual increment. We get rid of the natural losses and the fellings, and then we can understand the ozone effect on the net annual change in our forest standing stocks. And these were the kind of values that we were finding. So this is the gross annual increment without any ozone effect. This is the gross annual increment with ozone effect. This is kind of averaging out across the whole of Europe. And then this is the ozone effect after we've also allowed for removals from natural and felling harvest removals as well. And the headline figures, we found that if we had actually reduced exposure back to pre-industrial levels, then we would see an increase in European forest stem volume growth rates of about 9%. But if we allowed for those annual net changes in standing stocks, then the increase would be closer to 30%. And if we convert this into carbon sequestration, then we're also seeing increases around about 30% in the absence of ozone if we were to clean the air back to pre-industrial levels. So some key conclusions. Ozone causes a variety of injury and damage. We have a lot of evidence, North America, Europe, and increasingly Asia, but we have lots of areas where we don't have much information. There's been a lot of work to develop ozone metrics, but I still don't think we're really quite clear on which metrics are most useful for which situation. And perhaps we need to understand the location of specific ozone profiles better to decide that. And ideally, we would be able to understand not only the impact of ozone, but also the combined impact of ozone with other stresses such as drought, heat stress, and CO2 fertilization. And hopefully the development of different crop models with ozone damage functions can allow us to do that. And I would argue that we probably need new methods to develop to look at both crop yield, but also crop nutritional quality, and also carbon sequestration in forest trees. And then in terms of future research, just coming back to this kind of super pollutant issue, obviously, I think we still need additional experimental data. I mean, you can always have more data, but I think we definitely need to look at these data poor regions in Africa and Latin America. We need to be having that data to support the development of our existing and any new methods that we might be wanting to apply. And one thing that I haven't really mentioned too much, but we need to understand sort of different cultivar sensitivity better, but then also different tree types. We've got a lot of information about effects on temperate trees, but really not very much on tropical trees. And if we're talking about carbon sequestration, that's going to be a really big topic. We need models that better understand these combined impacts. And then all of this, I think, becomes really important as our policymakers are thinking about these super pollutants and wanting us to give them far better estimates of the actual impacts of ozone on vegetation so that they can weigh those off against mitigation strategies and really kind of push for the win-wins that you might see and the multiple benefits that you would get from tackling tropospheric ozone. So I think that's it. I hope that's kind of in time. And I shall try and stop sharing if I can manage that. Oh, right. That works.
Thank you. Yeah. Thank you, Lisa.
Thank
for an
you.
excellent summary. Yeah, so for an excellent summary of ozone. I'll open the floor for questions here. Anyone has questions, you can unmute yourself and ask, or you can type it in the chat, please. Hello. I hope everyone is still around. Friday afternoon, I do understand. Yeah. Yes, Gary.
Lisa, that was very good and well done, very comprehensive as well. It was great to see it, having some familiarity with it all, but it was great to see it. And I think you put it together. Lots of thoughts there and about, issues that you raised around metrics and, which are the appropriate metrics. But I think you probably got to the nub of it there with, how the how ozone concentrations are changing, where you compared the UK and the different drivers, the focus in, global north, I guess, is certainly America and Europe about reducing peak ozone, and then clearly as that expands. Sorry, that was all a preamble, just to say it was fantastic and very relevant. And I really like what you were doing around the nitrogen stuff, because I think, yes, it's both, I guess, quantity and quality. My question actually is probably linking more to iLEAPS in that sense. I just wondered, there's a kind of role here around the biogenic VOCs. I guess I'm just being a bit tangential, and I guess particularly with the forests is about what the role of the BVOCs are in this space as well, because obviously at one level they are reactive compounds that would reduce ozone, but obviously there are volatile organic compounds, and clearly in the NOx environment they lead to ozone production. So it's a very slightly complicated picture, but just your thoughts.
I don't know whether I've got any thoughts that would provide any answer to that kind of question. I mean, again, it's just something else that kind of gets thrown into the mix of something we need to understand better, I think. I mean, I know that there are some ideas or efforts, again, to sort of be further developing some of the models so that you can get better estimates of biogenic emissions. I mean, my understanding is that most atmospheric chemistry transport models will still be using Megan to give themselves an estimate of BVOCs. One of the things that I think could be possible is, especially as we're starting to develop these more photosynthetic based models for risk assessment, is you could also use them to make an estimate of BVOC emissions. Again, how accurate that would be, I don't know. So there's a kind of whole load of developmental work that would need to go on there. But then it probably becomes a little bit more of a consistent estimate of what the emissions might be and how they might also be related to concentrations and impacts as well. I mean, I kind of almost wonder, do we have time to be further developing all of these different models, given where we are in terms of things like, I mean, just the impacts, but also things in terms of near-term climate change? How much do we need to really understand, and how complex do our models need to be to just make sure that we have enough evidence to give to a policymaker to say, if you take this action, then it's probably going to give you quite a good benefit. And I think that's probably why I sort of come back to that, the super pollutant thing. And there's a lot of, I don't know how familiar people might be with this super pollutant term. I think I am, because I'm sort of within the CCAC space, and it's something that even us within the CCAC, we feel a little bit uncomfortable with it, because it's very much a simplification of ozone, which is quite a complex chemical pollutant. But it does seem to be gaining traction, and the traction it seems to gain is that policymakers are really asking, okay, well, what are the effects of ozone, so that we can weigh any mitigation of ozone against those effects to show that we're getting some multiple benefits. So I think almost a question back would be, how robust and accurate does our information need to be? So maybe how complex do our models need to get before we feel certain that we can say, you need to take this action and it's very likely to give you this benefit? I think there's a bit of a scientist, we kind of need to weigh that up a little bit more, I think, to help the policymakers out. But it'd be interesting to see what you think about that as well.
Yeah, no, I just come back a bit on that, because we've kind of had, that's quite we're covering a very broad space here. But I guess fundamentally, as you said right at the beginning, that if we could really get the win-win from air pollution and climate, that's obviously, I guess, the bottom line. I guess probably actually just thinking after I was reflecting as you were responding back to me about BVOCs, in one sense, it is a response to stress on the the vegetation, particularly forests. So I guess there is, there's some links there between those. I don't want to hog the space, but I think, I'd probably just say, and I guess the other thing I'd throw in, because I kind of know it's on my immediate thought, is about, at least in the Earth system, ozone damage, taking account of some of these other processes, does actually offset some of the expected carbon, gains from the carbon sequestration. So I think, there's probably slightly more to do, but obviously, we've got to get that. Do we have enough certainty, I guess, confidence in what we're saying to, that we've got the evidence to support what we're trying to say? Yeah, for sure, we could always improve things and always get new information. But I guess, are we 80-90% have we got 80 or 90% of the story? Not always going for the 100% for sure. I'll leave it there, because I'm sure others could ask.
Thanks, Gary. Lisa, there's a question in chat. Do you want me to read it out, or you?
I can get into the chat, I think.
Yeah.
Oh yes, okay. So this is talking about different emission reduction strategies. So, and then the effect that has on peaks and chronic levels. Which of these emission reductions would be more beneficial for crop yields? Well, that probably depends on which metric you're using to estimate the benefit for crop yields, I think. I mean, I think that there's probably more to be done to understand the local or regional ozone concentration climate. I'm not quite sure the best way of sort of referring to this, but that the kind of the ozone profile that you have in a particular area, then I think you need to sort of, once you've understood that, can work out which metric is most useful to use to understand what the potential impacts of that ozone profile would be on your vegetation. And then I think in terms of the emission reduction strategies, you'd probably need to work out, well, what's the driving force behind your policymakers to a certain extent in terms of what emissions they feel like they can reduce. And I guess the difference between the local and the global, we've got things like the global methane pledge, which in theory should be reducing global methane concentrations everywhere, but I'm not sure that the progress towards achieving the global methane pledge is actually that good. So maybe it is better to be thinking about those local emission reductions of NOx and VOCs. So I don't think I can answer the question. I think really what I was trying to do, I suppose, is say that we need to think more about those local ozone profiles or climates, understand them better, understand also how they're changing, because emissions will be changing anyway, irrespective of policy, and then sort of think about that in relation to the impacts and what might be the best metric to actually assess those impacts. So I think it's more a statement than being able to give a definitive answer. I think it is just something that we need to understand better and think about more in the future. I don't know if that helped at all.
You happy with that, Ronak? There's another question from Soreb, Lisa.
So how does chronic multi-decadal exposure to ground level ozone affect carbon sequestration potential for agricultural crops in the UK? So we don't often think so much about carbon sequestration in terms of agricultural crops because the crop is normally harvested on an annual basis. So really the main difference that you might see in terms of carbon sequestration would be a kind of what you'd hope, I suppose, would be a steady accumulation of carbon just in the soil, which is probably why we focused on forest trees, because you also have the carbon that's held in the tree in a forest system. That there has been work, I think, to sort of try and understand how ozone might affect things like root exudates, which will then affect the amount of carbon held in the soil within agricultural systems. I would say probably it's more important to try and get the forest carbon sequestration right before we worry too much about agriculture and ozone effects on that agricultural soil carbon sequestration. But it could be that that is having an effect, and maybe that is something that we should be more concerned about. And then there's a couple of there's sort of comments coming back, aren't there, I think?
Yeah, so I think Saurabh is still typing.
Yeah, and Ronak has said also complicated by the impact on human health as well. I mean, I think this is where, as a sort of ozone affects vegetation community, we need to be sort of trying to work out how to give the best information about what the ozone impacts on vegetation are, and then leave it up to the policymaker, you could say, to then bring that together with the human health effects and the effects of ozone as greenhouse gas to ideally formulate the best mitigation strategies to cope with all of those different impacts in the most cost-effective way. That's probably putting too much pressure on policymakers. There's a questioner, can you please explain same for forest? So is that in terms of carbon sequestration?
Carbon sequestration. Yeah.
Yeah, so I mean, just in very simple terms, we know that ozone reduces the amount of biomass that is held in forest trees. So if you reduce the amount of biomass in a large forest system, such as that across Europe, then the biomass that isn't in the forest will result in additional CO2 in the atmosphere, and that leads to this sort of indirect effect of ozone as a greenhouse gas, essentially. And the idea in terms of what we were doing was sort of trying to develop a simplified method, which meant that you didn't have to grow a forest over 100 years, but you could look at a particular year, see what the ozone concentration was in that year, have stats which are regularly collected under the IPCC to estimate carbon stocks and sequestration by country, and then use our dose-response relationship looking at net annual increment to give you an idea of the ozone effect on that year-on-year carbon stock that you know is held in your forest. So it's a kind of simplified method that we hope would give a bit more information to policymakers without having to do lots of complex ecosystem runs, which would take a long time. Don't know whether that's answered the question. There's more coming. Okay.
Yeah.
Right, that helped.
That's okay. Yeah. So I don't see any more questions in the chat and no more hands. So maybe we can just conclude and then go for a nice weekend.
Yeah.
Yeah.
Happy Halloween.
Yeah, happy Halloween, of course. Yes, my goodness. Yeah.